In this video, we're going to talk about suggested homework problems from 3.4. In 3.4, we're going to be talking about applications of the second derivative, specifically how we use the second derivative to find intervals over which the function is concave up or concave down. We're going to find points of inflection, and we're going to do the second derivative test for extrema. So let's go ahead and get started with this. So first question is number 3, and we're to look at this graph and to decide the intervals over which f prime of x is positive or negative, and f double prime of x is positive or negative on this interval 0 to 2. So the sign of f prime on 0 to 2, since the function has a positive slope the entire time, so f prime of x is greater than 0 on the interval 0 to 2. Second derivative, because the graph is concave down, concave up kind of looks like this, that fills up like a cup, concave down like this, upside down cup where the water will fill up. If it's concave up, the water will spill off of the graph. If it's concave down, just think about water pouring onto the graph, and does it spill off or does it fill up? So it is less than 0 on 0 to 2, since this is all the water that you pour on the graph would run downhill this way. So, all right, let's look at number 5. Number 5 asks us to find the intervals over which we are concave up or concave down by using the second derivative. So going to find the zeros of the second derivative to answer this question. And the second derivative has no zeros, so there are no places where the concavity is going to change. So it's going to have positive concavity everywhere. From negative infinity to positive infinity, we'll have a positive value of positive 2 for our concavity. So that's going to be concave up from negative infinity to infinity. Let's look at number 9. F of x is 24 over x squared plus 12. And I'll look at that as 24 times x squared plus 12 to the negative first to get started. Negative 24 x squared plus 12 to the negative second times a 2x gives me a negative 48x in my numerator and an x squared plus 12 to the second in my denominator. For my second derivative, I'm going to need the derivative of the numerator times the denominator minus derivative of the denominator times the numerator all over the denominator squared. Let's pull out some common factors on the numerator. So I have a negative 48 and an x squared plus 12 that are common. And that leaves me with x squared plus 12 minus 2 times 2x times x over x squared plus 12 to the fourth. When I divide that out, it gives me an exponent of 3 in the denominator. F double prime of x is equal to a negative 48 times x squared plus 12 minus 4x squared over x squared plus 12 to the third. F double prime of x is equal to a negative 48 times a negative 3x squared plus 12 over x squared plus 12 to the third is a negative 48 times negative 3 is a positive 144. X squared minus 4 over x squared plus 12 to the third. So f double prime of x is equal to 144 x plus 2 times x minus 2 over x squared plus 12 to the third. Zeros of the numerator x plus 2 equals 0, or x minus 2 equals 0, x equals negative 2, or x equals 2. Let's put those on the number line. Negative 2 and 2. Looking at our second derivative formula here, when x is less than negative 2, I have a positive times a negative as a positive in my numerator. The denominator will always be positive and won't change the sign of my numerator. So the entire fraction is positive, and that represents a concave up section. Between negative 2 and 2, like 0, positive times negative is negative. Again, the denominator won't change the sign of the numerator since it's always positive, and this section is concave down. For a number bigger than 2, I have a positive times a positive times a positive is a positive. Again, the denominator won't change the sign of the numerator since it's always positive here, and the function will be concave up in that interval. So we're concave up from negative infinity to negative 2, union 2 to infinity, and we are concave down on negative 2 to 2. On to number 15. 15 has the same instructions. Y is equal to 2x minus tan x. And we have a restricted domain of negative pi over 2 to pi over 2. That may be important later. So y prime is equal to 2 minus secant squared x. Y double prime is equal to a negative 2 secant x times the derivative of secant is secant tangent. So y double prime is negative 2 secant squared x tangent x, and this is equal to 0 when negative 2 secant squared x is equal to 0, or when tangent of x is equal to 0. This will never be 0 because secant has to have values that are outside of the values of negative 1 to 1 that are normally cosine. Secant squared is going to have to be greater than or equal to 1 specifically. So negative 2 times a value greater than or equal to 1 will be less than negative 2 and can never be 0. So tangent of x is equal to 0 only at x equals 0 in this interval here. So when I find my point of inflection, not there yet. That'll be the next problem. But I'm going to do my first derivative test here, or my second derivative test here. And this is negative pi over 2 to pi over 2. Pick a number like negative pi over 4 to represent this interval. And so, like I said, this piece will always be positive. This piece will always be negative. So this is a negative times a negative is a positive. So that's concave up. Again, a negative times a positive. And then this will be a positive. So this will be negative and concave down. So we're concave up on negative pi over 2 to 0. And we're concave down on 0 to pi over 2. start to talk about the next concept in number 15. It's going to be something called a point of inflection. And those zeros of the second derivative will stick those x values back in to the original function, calculate them to get an ordered pair, and that will be called a point of inflection. If you are going to talk about economics principles with this, this will be called the point of diminishing returns. So it'll be an important point for you to know in those economics applications. You get a few of those problems in the textbook, but not as many of them because this calculus course is intended more for STEM majors, where the applied calculus course is going to focus more on those economics principles and applications. So let's go ahead and take the first derivative and take the second derivative. Set it equal to 0. 6x is equal to 18. X is equal to 3. So 3 is, I'm going to have two things to do here to discuss the concavity. So I use my second derivative test to do that. And when I put a number less than 3, like 0, into my formula for my second derivative here, negative value making this concave down, and then bigger than 3, I get a positive value making this concave up. I also want to find f of 3, which is 27 minus 9 times 9 plus 24 times 3 minus 18 is 27 minus 81 plus 72 minus 18. So 27 minus 18 is 9. Negative 81 plus 72 is a negative 9. 9 minus 9 is 0, giving me a point of inflection at 3, 0. And we set here concave up on 3 to infinity and concave down on negative infinity to 3. All right. So at number 25, it has the same instructions as 17. F of x is equal to 6 minus x over the square root of x. Because I'm dividing by that monomial, I'm going to write this as 6x to the negative first minus 6x to the negative 1/2 minus x to the 1/2. I'm just going to think of that as x to the negative 1/2 and multiply through in the top. So f prime of x is negative 3x to the negative 3/2 minus 1/2 x to the negative 1/2. And f double prime x is equal to 9/2 x to the negative 5/2 plus 1/4 x to the negative 3/2. So f double prime of x is equal to 1/4 x to the negative 5/2 times 9 times 2 is 18 plus x to the first, which is equal to x plus 18 over 4x to the 5/2. Remember, my domain here is x has to be greater than 0 because I can't have a 0 in the denominator and I can't have a negative inside of the square root sign. So x plus 18 equals 0, yields an answer of x equals negative 18, which is not in my domain. And I can't have, I'm only interested in where f double prime is equal to 0, which is the 0 of the numerator. So no critical numbers, or no points of inflection, sorry. which means it's never going to change concavity. So when I go from 0 to infinity, and I look at my second derivative here, I only need to stick in my favorite positive number here. Doesn't matter what it is. I'll choose 1 to make that denominator simple. So 19 over 4 is a positive number. So this is concave up from 0 to infinity. All right. Looking now at number 31. Says f of x is equal to 2 sine of x plus sine of 2x. It's on the interval from 0 to 2 pi. So f prime of x is equal to 2 cosine of x plus 2 cosine of 2x. F double prime of x is a negative 2 sine of x minus 4 sine of 2x. And I'll use my double angle identity here to get rid of that sine 2x. Before I set this equal to 0. And I'm going to factor out a negative 2 sine x. It's going to be 1 plus 4 cosine of x. So negative 2 sine x is equal to 0, or 1 plus 4 cosine of x is equal to 0. Sine of x equals 0, or cosine of x is equal to a negative 1/4. So x is equal to a value of 0 or pi or 2 pi, since these endpoints are included. But I really don't want the endpoints. My point of inflection needs to be in the middle of the graph. So I'm only interested in pi there. And now this is a bit more interesting. I'm in quadrant 2 or 3. So I'm actually going to think about the positive version of this and add it and subtract it to pi. So x is exactly equal to pi plus or minus our cosine of 1/4. And I'm going to approximate that with my calculator. So pi minus arc cosine of 1/4. Make sure you're in radian mode before you do this. And I am. And to 3 decimal places, this is 1.823. X is approximately going to change this to a plus now. 4 point, and then that's 460 when I round. Don't use these rounded values in your calculations for your point of inflection. Use the exact values so that you don't get rounding error on top of rounding error. So f of pi is exactly equal to 0, because 0 plus 0 is 0. So that gives the point pi 0. Let's go in here and say second derivative is negative 2 sine x times 1 plus 4 cosine x, like that. And then my table here, I'm going to use pi minus our cosine of 1/4. I'm sorry, I didn't want that function, I wanted this one to sine x plus sine of 2x, everything else, because I want the y value. I already knew that it equaled 0. All right, so this is f of pi minus arc cosine of 1/4 is approximately 1.452. When we get it to 3 decimal places, and f of pi plus arc cosine of 1/4 is the negative version of that. So points of inflection are at pi, 0, then approximately 1.823, 1.452, and 4.460, negative 1.452. I'll use those approximations for my test for concavity because I don't need the exact numbers on my number line here for that, since I'm picking numbers that are bigger or smaller. So here's pi in the middle. Here's the pi minus the arc cosine value, and here's the pi plus the arc cosine value here. And then this is 0 to 2 pi for my endpoints. So let's go ahead now and go into my second derivative equation, which was, this is what I was starting to type in before. I just wasn't ready for it yet. So something between 0 and 1.8 something. So I'll pick 1, and that's negative, and concave down, something between 1.8 and pi. I'll pick 2, and that's positive. Concave up, something between pi and 4.460. I'll pick 4, and that's negative. And concave down, something between 4.460 and 2 pi. I'll pick 5, and that's positive, and concave up. So we're concave up on the interval from pi minus arc cosine of 1/4 to pi union pi plus arc cosine of 1/4 to 2 pi, concave down from 0 to pi minus arc cosine of 1/4 union pi to pi plus arc cosine of 1/4. The textbook is probably going to use the approximations here and say that we're concave up from 1.823 to pi union 4.460 to 2 pi, and concave down from 0 to 1.823 union pi to 4.460, like so. Okay, that was 31. Let's move on now to 35. And we're going to use the second derivative test to find extrema if we can. So the main issue with using the second derivative test is going to be if the second derivative is undefined. Then we'll need to go back and use the first derivative test. That won't happen on the smooth curve though. It's a polynomial. So I need to set this equal to 0 to find my critical numbers. And I'll need those critical numbers to plug into my second derivative. So now I'll find my second derivative, which is 6x minus 6. I'll factor out that 6. So f prime of 0, 6 times 0 minus 1. 6 times -1 is -6, which is less than 0, which means that I have a local maximum there. When my second derivative is negative, the critical number for the slope is 0 represents a local maximum. If I have a concave up piece, the part where the slope is 0 represents a local minimum. So that's what I'm going to have next here, f double prime of 2, 6 times 2 minus 1, 6 times 1 is 6, which is greater than 0, so there's a local min there. And I need to find f of 0, which is clearly 3, since that's the y-intercept. I need to find f of 2, which is 8 minus 3 times 4 is 12, plus 3. 11 minus 12 is a -1. So this gives me the point of 0, 3 that is a local max. And a local min of 2, -1. So number 43. F of x is equal to cosine x minus x. F prime of x is equal to a negative sine x minus 1. Set that equal to 0. Negative sine x is equal to 1, and sine x is equal to a -1. I have a restricted domain here of 0 to 4 pi. And so this is going to be x is 3 pi over 2, or 11 or 7 pi over 2. For my critical numbers, f double prime here is going to be a negative cosine of x. Write that in just a second. F double prime of x is equal to a negative cosine of x. So f double prime of 3 pi over 2. Cosine of 3 pi over 2 is 0, -0 is 0. So that tells me that this is a point of inflection, not an extreme value. Same thing with f double prime of 7 pi over 2. Is that it will also equal 0, so that's a point of inflection, not an extreme value. Let's take a look at this graph to see what's going on. So cosine of x minus x. Oops. Let's go back here and insert these parentheses. Cosine of x minus x on Zoom trig. And then I'm going to make my x max go out to 4 pi here. There you go. And you can, let me zoom out just a little bit more. So you can see the 2 cycles that are going on here, where we have a point of inflection here at 3 pi over 2 and another point of inflection down here at 7 pi over 2. These little turns in the graph, but it's decreasing, then continues decreasing, then continues decreasing. So there's no change in sign in the first derivative. Therefore, there's no minimum or maximum values. So there we go. Let's go ahead and look at 53 here. 53 tells us to use the information that's given here to sketch a graph with the following characteristics. I had to fix some things here that were inconsistent in the printout with what was in the book problem. So let me write what I have from the book. But it was listed this way. Okay, so if it's always negative for the concavity, I'm thinking something like a parabola that opens down, and I have x-intercepts here at 0 and at 2, 1, 2. I have a turning point in the graph, a local minimum or maximum at x equals to 1. That's going to be a maximum because at 1, the concavity is going to be negative. So I need this to be a maximum point. And let's just check how my slopes pan out when I do this. And I'm trying to, as best as I can, graph this right here is what I'm going for, or something like that. That's a constant multiple of that. And let's see here. So positive slope when less than 1, yep, that's a positive slope. Negative slope when greater than 1, yes, that's negative slope. So this parabola that has a maximum value x equals 1 has x-intercepts at 0 and 2. Just a sketch, not an awesome drawing, but we can show that maybe better with the calculator here with this function x squared minus 2x, zoom 6, negative of that, sorry. Second, insert negative and make that positive. There we go, like that. So it's increasing, then decreasing, has a maximum value at 1. It'll have a maximum value at 1, 1. And decreasing from 1 on. There we go. So let's look at number 55. And again, just copying what I have from the book, which the list is a little different here, and I don't want there to be any mistakes. So I have f of 2 is equal to f of 4 is equal to 0. F prime of x is less than 0 for x less than 3. F prime of 3 does not exist. And then f prime of x is greater than 0 for x greater than 3. And f double prime of x is less than 0 when x is not equal to 3. So no value for the second derivative at 3 because there's no value for the first derivative. Once one of the derivatives doesn't exist, then none of the subsequent derivatives will exist either. So with the first derivative not existing at 3, I'm thinking about some kind of a sharp point. Let's look at zeros at 2 and 4. I think that there's something going on interesting on this line that's a sharp point, and the concavity is going to be down. So water is going to be spilling off in both directions. So I'm thinking something like this. And see if that tracks. So slope is negative for x less than 3. Yes, it is. Slope is positive for x greater than 3. Yes, it is. Concave down, less than 3. Concave down, greater than 3. Can't define the concavity at x equals 3 because the first derivative isn't defined there. Since it's a cusp, and there's my sketch. Let's move on to this last problem here. And we have this vase here that we want to consider the function of the depth of the water versus time. So I have time here. I'm starting at time equals 0. I'm starting at depth equals 0. I'm going up. So the depth is going to see how it reaches this bulge here, and then it has another turn there. So these are going to be interesting points to me where these turns are in the vase, both where it turns in and where it turns back out here. So the depth of the water is increasing pretty quickly here, and it starts to slow as it has more width to fill up. So it fills up fastest where there's the smallest radius. So it's going up, but then going up at a slower rate. It's kind of going to stop there for a second, and then it's going to turn. It has a point of inflection there. So this is going to go from concave down to concave up, and it's filling, and the rate of change is increasing here because the radius is getting smaller. We'll notice it feels like it is going to fill up really fast here, and then it gets to this point where it turns, and we're going to again have a point of inflection, and it's going to be filling, but at a, so this is concave down, then concave up, and then we start to have another concave down piece here. I'm not drawing this very well, but kind of like that, that there's a point of inflection here where it changes from concave up to concave down, but it's still at an increasing rate. It's always increasing. It's just that it kind of changes here, how quickly it's filling. So let me see if I can put that into words here. So does the graph of the function have any extrema, which is question B? No, it does not, because the depth of water in the vase is always increasing. Or you can say it's non-decreasing. Let me say it that way. It's non-decreasing. Right? So there's no extrema. Interpret the inflection points. So again, I already told you that it has to do with these bulges here. And so this is going to take a lot of words, but it's what I already showed you in the picture and kind of what I tried to draw with the graph. The rate of change of D is decreasing until you reach the widest point of the vase, which is right here that I put those dots. Then the rate of change in D increases until you reach the narrowest part of the vase, which is what I marked up here, the narrowest part of the vase. Then the rate decreases until you reach the top of the vase. All right, so that's it for this video. We'll come back next time and we will talk about 3.5. See you for the next video.